This week is Supersymmetry week. We have two days on this. I think basically what I'm going to do is spend today on terminology and formalism, and Thursday on constructing the supersymmetric extension of the standard model and LHC style stuff. In preparing it, it's clear that there's yet again all too much to do, and this is actually very superficial, and there's a lot of stuff I'm going to just skip over. But nevertheless, I think we can actually accomplish something. We can get through all the terminology, what it means, what the basic stuff is. It's not enough to actually sit there and do calculations without some more work, but I think it should be cultural level anyhow. Okay, so the first thing we have to do is transition from Dirac fermions to Weyl fermions. Okay, so these are two-component objects. And if you remember, we have these projectors, PL and R is 1/2, 1 plus or minus gamma 5. And if we have a four-component spinor, so the Dirac guy, 4 components, let's call it upper and lower. Those are each 2 components, upper and lower components. If we take PL on psi, that's U plus L, actually it's U minus L, sorry, U minus L, U minus L with a minus sign there and a 1/2 out in front. So if I take the projector, I've got 2 identical 1-component objects. If I take the right projector on psi, I get 2 identical 2-component objects, 1/2. It's U plus L, U plus L. Okay, so we can just call these guys 2-component spinors. I would call this C minus C. This chi, chi. And so these C and chi are the 2-component objects. Okay, so that's the basis for all this supersymmetry work. If you start with a Lagrangian, the Dirac Lagrangian is L equals psi I d slash minus m psi. You can see how it decomposes into these 2 guys. So we're going to define, let me just do it up here. So define sigma mu is a 4-vector, which is 2x2 matrices. So actually, sigma mu has a minus sign there, and sigma bar mu is the same thing, 1 plus sigma. And those are relevant because if you just think about decomposing psi, the spatial components are off-diagonal ones, mixing tops and bottoms, upper and lowers, and they are proportional sigmas. So when I do this decomposition, I get time derivatives acting with the 2x2 unit matrix, and I get space derivatives acting with a sigma matrix. Okay, so the Lagrangian turns into it's C dagger I sigma mu d mu C, sorry, plus chi dagger I sigma bar mu d mu chi minus m c chi plus c dagger chi dagger. Okay, so mass terms mix the two chiralities. That's, we always know that. But this is what it looks like. The more important, these guys are the things that are the two-component Weyl Lagrangians. Okay, so they involve the sigma and sigma mu nu. Okay, so let's write out the first supersymmetric model. That's the Wess-Zumino model. Okay. Wess-Zumino model is a massless complex scalar and a single Weyl spinor. Okay, so the Lagrangian is just d mu phi star d mu phi plus c dagger I sigma mu d mu c. Okay, so there's our Lagrangian. If we actually count degrees of freedom, they actually don't match at this stage, and this is relevant for what we do later. The complex scalar is 2 degrees of freedom. Complex spinor is 4, right? Because it's complex and it's 2 components. But nevertheless, that's what it is. We'll solve this one in a little bit. Okay. This has a hidden symmetry that you don't see at the start. The supersymmetry is the following. We're going to try transforming the scalar into the fermion. And actually, if you'll let me, most of the rest of my notes call this psi, but it's still a Weyl spinor. So let me go back to psi. Nobody's copied it down. That's safe for me to do, just so that matches the rest of my notes. But you remember it's a 2-component guy. Okay. If you want to do this, you have to use Grassmann numbers for the transformation. And we saw Grassmann numbers when we did path integrals. I chose not to review it to start off here. But basically, we're going to look for something that looks like delta psi is some Grassmann number. Delta phi is some Grassmann number times psi. That makes sense. Fermion's anti-commute, Grassmann numbers anti-commute, phi's commute, so that will work out. Delta phi stars has done the same, epsilon dagger, phi dagger, just complex conjugate. So we're looking for a transformation that looks like that. The thing that you can see, if I just do that transformation, is that derivatives aren't going to match up. See, the phi piece has 2 derivatives, the psi piece has 1. So let's just if I take delta L of phi, it's epsilon d mu phi star d mu psi plus epsilon dagger d mu psi star psi dagger d mu phi. So that's just the change up there. Okay. I now want to take some variation of psi in terms of phi that cancels this off to have a symmetry. And it's going to have to involve a derivative because there's only one derivative in the Lagrangian. So that's the first thing. Delta psi involves a derivative. Okay. And the answer that works is delta psi is I sigma mu epsilon d mu phi star. Actually, d mu phi dagger, I guess, is what I have in my notes. Okay, and you can sort of see that if I take a variation over here with this and the sigma matrices can cancel, and I would then cancel off this guy here with that piece. Okay? Delta psi is minus I. I have sigma mu epsilon dagger d mu phi. Okay? Then, if you do this, delta L total is 0. Okay, so the supersymmetry transformation is delta, let's call delta epsilon on phi is epsilon psi. Delta epsilon on psi is minus I sigma mu epsilon d mu phi. That's the SUSY invariance. Okay. The fact that it's a derivative there ends up being important in the overall logic of it, because it brings space-time into something. It's not like an internal symmetry where you just rotate the fields. Here we've suddenly got the derivatives entering. Derivatives end up like momentum. We're going to see that's an essential part of SUSY. Okay, the two of these guys don't commute. If I take delta epsilon 1, delta epsilon 2 minus delta epsilon 2, 1, epsilon 1, delta epsilon 2 on phi, it equals the following. It's epsilon 1. So you can sort of see what's going to happen. The first one gives me a psi. The second one acting on the psi gives me a phi back again, but with a derivative. Okay, and so this ends up being epsilon 1 sigma mu epsilon 2 dagger minus epsilon 2 sigma mu epsilon 1 dagger times I d mu phi. Okay, so that part's the important piece. There's another piece which at this stage seems like a technicality, but if I do the same thing on psi, I end up getting the same thing. But if you go through the steps, you use the Dirac equation. Okay, so end up using the Dirac equation to get there. That's at the moment of curiosity. Okay. Questions, anybody? No. Okay. So if we have an invariance, we have then conserved currents and charges. Okay. So Noether's theorem can be used then to get the conserved currents and charges. Let me just give you the answers. There's the conserved current is sigma nu sigma bar mu psi d nu phi star. Okay, and there's the Hermitian conjugate is okay. These guys are two components. Because psi is, so you might put a little Dirac index alpha on that. That alpha is 1. Okay. So the two component charges, so they're fermionic charges. They have one boson, one fermion, so they're overall fermionic. And so two components. The charge, let's define the charge. It's also, so it's the integral J0. It's also two components, so you can put an alpha on it if you want. D3x. And the place I use as a reference included a square root of 2 in there that influences a factor of 2 later on, but it's conserved either way. Okay, so you can also, for relevance, you can also define operators, which is p mu as an operator is the Hamiltonian, and the momentum operator, this is T0I. And these guys are, written as always in terms of pi phi plus del phi star del phi. So the Hamiltonian, the momentum are operators, the usual Hamiltonian that we have. They're actually not that well. Let's show how it ends up getting used. The immediate use of this is in defining an algebra, so the supersymmetric algebra. Okay. If I take two of these charges, Q and Q dagger, and anti-commute them. Okay, so there's just a bunch of technology to do that. There's a couple places where you get non-zero things. You get, when you anti-commute two sides, you get a delta function. When you anti-commute phi, d0 phi with phi, you get a delta function also, right? Because pi is d0 phi. So there's when you anti-commute psi or commute d0 phi, and when you take this anti-commuter of the product, it turns into the anti-commuter of psi's and the commuter of phi's. Okay. Anyhow, so you can work that out. It turns into 2. Here's my 2 that from that normalization. Sigma mu times the Hamiltonian and momentum operators. Okay, that's a crucial piece. This is foreshadowed in what we did before, in the fact that when I act with the symmetry twice, where did it go to? When I act with the symmetry twice, the symmetries don't commute, and they give you something proportional to the derivative operator. that's really the same statement as taking the charges twice, giving you the derivative, the Hamiltonian and momentum operators. So one case is the matrix elements, the other case, it's the operators. Okay. And Q's with Q's commute, anti-commute, I'm sorry. Q's daggers with Q daggers, anti-commute. And if I take, I'm sorry, this is Q commuted with the momentum operators, ends up commuting. That one's actually a little tougher to show, but it comes out. In a way, this one is the one that says that these charges can be conserved charges at the same time as energy and momentum can be conserved. So this is Q, E, and P all conserved. Okay. And sometimes you know that's the case. That's because the original Lagrangian obviously has conserved energy and momentum. We show that it has a charge, so that had better work out. Okay. So the things to point out here is that the SUSY algebra mixes up space-time symmetries, or mixes with. That's a key feature. The other thing to point out is that having found it in this simple model, the goal of much of the rest of the work is to generalize the algebra to interacting theories. Okay, so there's the discovery of supersymmetry, if you want. That's the Wess-Zumino model, where you can just by hand construct all these things. And we could all do that part. At this stage, we start entering into the technology game. Okay, so there's a whole host of supersymmetric technology built up. The first step of this is a trick involving auxiliary fields. Okay. So, and it is a trick. We're going to add to the Lagrangian a new field, but it's going to be trivial. Okay, so the Lagrangian is going to be F star F. Okay, that's a fancy Lagrangian. The Euler-Lagrange equation is F is equal to 0. So we haven't added too much, but we're going to give this F a transformation under this supersymmetry. So we're going to take, when we do the supersymmetry transformation, we're going to take delta F is, what is it? It's epsilon dagger sigma bar mu I d mu psi. Okay. If you do that, then we get this delta epsilon 1, delta epsilon 2 trick. On psi equaling that stuff without using the Dirac equation. Okay. F, yeah, well, you know, the idea is that they get removed at the end. So we stick them in, we give them this transformation property, they make our algebra simpler because of this business here. I don't have to use the equations of motion. And then I remove them at the end. They end up being useful in the construction because they make the symmetry more explicit. And so some of the terms we do with chiral superfields, they're useful there. Okay. Whether they're off-shell, I don't know exactly how to say it. In the Lagrangian, there's no on-shell, off-shell. Just like the Dirac field. Remember the Dirac Lagrangian, psi bar I d slash psi. If I use the equation of motion, the Lagrangian would vanish. Okay, so it's not on-shell, off-shell. Okay. The trick here is the degrees of freedom. Okay, so remember I pointed this out before. Phi is 2 degrees of freedom. Psi is 4 degrees of freedom. But the Dirac equation reduces that. It says the Dirac equation is I sigma bar mu d mu psi equals 0. So that reduces to 2 degrees of freedom. Okay, so after using the Dirac equation, they're the same number of degrees of freedom. Okay, so 2 of them get thrown out. But if I don't use the Dirac equation, we can do psi is 2, f is 2, psi is 4, so the fermion and boson degrees of freedom match without using the Dirac equation. And then the equations of motion later on remove f totally and remove psi goes to 2 degrees of freedom. Okay, so the equations of motion then remove half the fermions and half the bosons symmetrically. So it's a more symmetric construction to begin with. Okay, so that's the point of that. Okay. All right. Piece 1 of technology, the auxiliary field. Piece 2 of technology is superspace. So this is going to endow space not only with the coordinates, but with fermionic variables also. So we're going to take 4 new degrees of freedom, 4 new variables, 4 new coordinates. So there's going to be 2 of them that are called thetas and 2 of them that are called theta bars. So the theta has 2 indices, alpha 1, 2, likewise. Theta bar, they're Grassmann variables. Okay, so if I take theta with theta is 0. It's all combinations there. But now we're going to build up superfields that depend on the coordinates. So it's called phi. It'll depend on x, theta, and perhaps theta bar. So there'll be some that depend only on theta, some that depend only on theta bar, some that depend on both. Okay, then the fermion part of these fields is associated with the Grassmann coordinates. Okay, so for example, the fields that we saw there before, they're all going to sit in one superfield, so they're really just different parts of the same field rather than different fields. Okay, the chiral superfield is the first one. Okay. This is going to be a field that it only depends on two of these coordinates. So it'll be x and theta, no theta bar. Okay, and that's why we sort of have these two sets of coordinates. The thetas are associated with one chirality, theta bars with the other. Just like when we had the Weyl fermions, we took two of them and made them into psi's and two into chi's. We separate out the left and right chirals. Okay. Well, the field then, since these are Grassmann, can only contain a few powers of theta. It can contain theta, of course. It also can contain theta squared. Theta squared. Okay, if you have two thetas, now thetas are Grassmann. Normally, if you square a Grassmann, you get 0. But this is a two-component Grassmann, so there's two variables in it. So theta is theta 1, theta 2. So there's two of them. So I can get up to that order. So it's sometimes, theta A, theta B, it has to be antisymmetric in those two, epsilon A, B. So when you see theta squared, it means the upper times the lower. It has to be an antisymmetric combination since the Grassmann. Okay. But then that's the furthest you can get. You've got two Grassmann variables. You can have no Grassmann, one Grassmann, and this theta squared. Okay. So phi, the Grassmann, is going to be, starts off with a scalar field, which is a function of x, of x. The first term in the expansion in terms of is theta alpha, psi alpha. So those two work there. So most often that spinor sum is unexpressed, and then it's theta squared times f. Okay. So they all fit together in the same field. And if you do a supersymmetry transformation, delta epsilon on phi, it's d by d theta plus 2I theta sigma mu d by dx on phi. Okay. So in a way, it's like translating in the bosonic coordinate and translating in the fermionic coordinate. And if you work out what that is, that gives you all the variations that we wrote down before, in size in terms of phi's and f's in terms of size, etc. Okay. So this allows the invariance to be explicit and contain, combine all things into. There are some tricks that I don't know well myself and certainly don't have time to get into about taking the complex conjugate. This is right chiral. If the other one is left chiral, this one has the opposite chirality. And there's some technology here because this would naturally be expressed in terms of the theta bars, and so going from theta to theta bars, as I say, I'm not keen on it myself. But the end result is that if you want to write out the action for the Wess-Zumino model, for example, I take the integral d3x, d2 theta, d2 theta bar of phi star phi, these chiral superfields, and that turns into then the integral. We started with d4x of the Wess-Zumino Lagrangian. So the terms that we had before fall out from taking that one, which, if you follow through the details of the invariance, becomes explicitly invariant and simply invariant in a way that you don't have to go through all the calculations that we did to start with things with. Okay? So, there's one superfield. Chiral superfields contain only one of these two Grassmann variables and only one of the chiralities. Okay. The other one that is the vector superfield. Okay. This comes for wanting to add vector particles. So this would be one that, for example, might have a gauge boson in it, and then it has to have a supersymmetric particle, which is the gaugino. Okay. If you write out the vector field in usual notation, the gauge interactions, we'd write out a quarter Fa mu nu, Fa mu nu. We'd have to write out the fermion part, which is lambda dagger I sigma bar mu d mu lambda. There's actually an A here and an A there, and this is a covariant derivative in the adjoint representations. So actually, I guess I really should make this AB, and this is lambda B. The covariant derivative in the adjoint looks like d mu AB is d mu delta AB plus IG F A B C A mu C. Okay, so there's the covariant derivative. And here, if we do the same, go straight to the auxiliary field trick, there's going to be some auxiliary fields D. These are the D, these end up being D terms that you hear. And this, you can work by good old-fashioned methods, you can get up the SUSY transformations. I don't know, delta A mu, A mu, 1 over the square root of 2, epsilon sigma mu, lambda A plus lambda A sigma mu epsilon, delta lambda is let me just forget the details. It has an F mu nu in it. You can sort of see that it has to do that because if I do a variation on A here, I'm going to get F times lambda. So I do a variation of F of lambda, I'd better get something that looks like F. And there's also a piece that looks like epsilon dA, and then there's a delta D is d mu lambda, and yeah, there's an antisymmetric combination on d mu lambda. Yeah, sigma bar. Things like that. Okay, so let's, it's not, I'm not really being so precise anyhow, so let's just leave it like that. You can sort of see how it could work out. You can also see, again, it's the same sort of thing, that the scalar turns into the fermion turns into the derivative of the boson, and the auxiliary turns into the derivative of the fermion. So again, you get derivatives entering left and right. This ends up with the same SUSY algebra. You can define charges again, the same SUSY algebra. Okay? Superfield notation. All right, so all right. The vector superfield doesn't have any intrinsic chirality. It's a function of theta and theta bar. So it has more terms in the expansion. So what I have is minus theta sigma mu theta bar a mu plus theta theta bar lambda bar theta lambda plus 1/2 theta bar d. Okay. Matrix indices are actually suppressed on this, so D, or A for that matter, is the group matrices times dA. Okay, so likewise A has a matrix embedded in it. This ends up generating the gauge interactions. Okay, if you take integral d theta, d squared theta, d squared theta bar, if I take this chiral superfield and I write between it either the 2GV, that's the vector superfield, psi. Okay, now the fact that it's an exponential isn't as scary as it sounds. It's the one piece is the obvious one, that's the old Lagrangian. And then when you start expanding this, you can only get so far in the expansion, right? Because you've got too many Grassmann variables here, you can't go to very high orders. You can get up to v squared. V squared is useful for theta, theta bar, theta, theta bar terms. Beyond that, there's no terms. Okay, this turns into the Wess-Zumino Lagrangian, but with usual derivatives turned into covariant derivatives. Okay, so, you know, when you had this, the A piece between two fermions, you end up with the term that gives you the covariant derivatives, etc. Okay? You get one extra set of pieces. You get also pieces that look like g times the square root of 2 phi star lambda psi minus lambda psi dagger phi. Okay, so what are those guys? Those are, so this is a fermion, the partner of the gauge boson, and the scalar. So these are just the supersymmetric variants that look like the following. So if we have psi, psi, A, then there's an interaction psi, phi, lambda, where lambda is the partner of the A. So those are the Gaugino interactions. Okay. So it's, and then there actually is one other term. It's G phi star times D phi. This enters later, and maybe even today, into D-term supersymmetry breaking. Okay, so that's the auxiliary field for the. At the moment, all it does is it complicates the equations of motion for the D terms. Remember, they normally D is equal to 0. Now when I get the equations of motion for D, D is going to equal phi star phi. Okay. Last feature. The superpotential. Okay. There's something that if you look at what all the terms we built up terms that have gauge interactions between the gauginos, the partners of the gauge bosons, and the particles. The things that we don't have is we don't have any interactions between the different chiral fields. So that they were just free. So they take the chiral supermultiplet. We don't have any interactions there. And so in particular, we need things like Yukawa interactions. We need, be phi bar psi. Things like that are interactions that we normally build up. That involves free fields, all of which live in the chiral supermultiplets, so how can we do those? Now, the answer is the superpotential. Okay. So, let's if we took the following. Okay. Let's imagine I have a few of these, phi 1, phi 2, phi 3. And I integrate d theta squared. Remember, these things depend only on x and theta, so the theta bar piece of that is irrelevant. So it's 3 of them. Well, that's something that you might think gives us Yukawa terms, and in fact it does. You know, you would get terms like, so it's the integral d to theta, phi 1 theta, psi 2 theta, psi 3. Yeah, so there's a bunch of terms, plus dot dot dot, plus dot dot dot. There'll be terms which I want to highlight as phi 1, phi 2, f3, theta theta, plus dot dot dot. Okay. So here's a way you can write out interactions like this. This looks good for Yukawas. Okay, so here's a Yukawa. Here's a term that after I do the integration ends up being f phi phi. Terms like that. Okay. So you can generalize this. The basic idea of the superpotential is that it depends only on theta. Okay. So if we take a W of phi I, okay, they can have various terms. It can have a term that's linear, so the linear term has some coefficient. You can have terms that look like masses. And it can have these Yukawa-like terms, G, I, J, K, phi I, phi J, phi K. So but the trick is there's no phi stars in it. That's important. If you do this, then the Lagrangian, that's the integral d theta, d2 theta of the superpotential is, all right, so let's, one that has to, there's a lot of terms you have to work out. It turns out to have the general form. It's the derivative of the superpotential with respect to phi I times fi plus the derivative, or it's minus a half, sorry, minus a half derivative of the superpotential with respect to phi I, with respect to phi j, psi I, phi j. Okay, that's, you can see these two terms here. You can see this f term here you can get from the derivative with respect to phi gives me, in this case just gave me 1. If I took phi 1, I get phi 1, phi 2, phi 3. So this term came from the first term. The Yukawas come from, if I took the superpotential phi 1, phi 2, phi 3. It starts off with lowercase phi 1, phi 2, phi 3. So if I took two of the derivatives with respect to that, I would get 1 phi. I multiply by psi phi, I get the Yukawa pieces. Okay. So this gives masses in Yukawas. This gives F terms. Okay. So again, what that does is it changes the F equations of motion from just being F equals to 0 to being things like F is phi star phi, or is phi phi. Okay. So D terms and F terms. Okay, our lightning buildup of this. These are things you hear all the time when you hear about supersymmetry breaking. We'll next time say a bit about how they enter supersymmetry breaking. But after we've added interactions, we have the Lagrangian is a bunch of things. Well, we have Fi. That was the auxiliary field that we put in, plus the term we just wrote out there is the derivative of the superpotential with respect to phi I, Fi. Okay, so we've got those two terms. Then we have the D term, which is 1/2 dA, that's running over the gauge indices, plus G phi star D phi, which came from the adding the gauge terms to the interaction. So those are our pieces. Actually, a comment I forgot to say about the superpotential is that the superpotential is not the potential, right? Let's go back and say that here. When you write this down, you might think this is like writing down V of phi. It's not V of phi itself. V of phi is this combination that comes from doing the integration over the Grassmann variables, Grassmann coordinates. So the real potential is things like the second derivative of the superpotential times size, or the first derivative times F. So this is the potential, that's the superpotential. One constructs the other, but it doesn't, don't think of the superpotential as being the interactions themselves. All right, so now back to D terms and F terms. So our auxiliary fields end up then with those interactions, and then you integrate out the D and F. Okay. The equations of motion then turn into F dagger is dW d phi. dA is G phi star TA phi. Okay. If you substitute back in, then the Lagrangian for the remaining fields has terms that look like dw d phi I dagger dw d phi I plus or minus a half g squared phi star ta phi star ta phi. And this guy is the real potential for the remaining fields. Okay. Okay. If you go back up to these definitions up here in the superpotential, you can see that the derivative of w respect to phi, where's my super, oh there it is, w respect to phi has terms that, well, they could be constants, they could be have one phi, or they could have two phi's in them. So when you get down here to these, to the f terms, this will give things like m squared phi star phi. It will give terms like g squared phi star phi squared. So quartic interactions. So quartic, lambda phi to the fourth interactions come out of the superpotential. But it also then gives you things like g psi bar psi phi. So Yukawa interactions also come out of that. They come out with the same coefficients, so the supersymmetry gets manifested in these identities, the coefficients. This type of term also gives you a lambda phi to the fourth type term. So the d terms give you lambda phi to the fourth terms. Okay. So there's the technology in a whirlwind tour. If we do model building, so if you wanted to build a supersymmetric model, what would you do? Now, step one is you choose your number and type of the chiral superfields. So we take, phi I, psi I, fi's, and the vectors is the equivalent of choosing the gauge interactions. Lambda A, and D. The one is by the particle content. So if you're trying to do the standard model, you need to choose a chiral superfield for each quark type, quark and lepton, and a vector one for each gauge interaction. The next thing you do is you write the most general superpotential. And so W is this L phi plus M phi I phi j plus G I j k phi I phi j phi k. Actually, comment on stopping there corresponds after you've done the construction up above to stopping in renormalizable terms. Okay, so You want to stop at cubic order so that when you form the interactions, you get renormalizable ones. Okay, so the third step is you write the kinetic energy piece. You write integral d2 theta, d2 theta bar, phi dagger, e to the I to gv, phi, with a vector superfield. So that gives you your kinetic energies plus gauge interactions plus gauge enos plus d term. Okay. Okay. Step 4 is you get your potential from the superpotential. You write integral d to d2 theta. W is this dw d phi times f plus psi d2w d phi I phi j. And then the last thing you do, 5, is you integrate out d and f to give d terms and f terms, and that adds to the Lagrangian dw d phi I. Okay. Those are then the scalar potentials that end up right. Okay. So there's your construction of Lagrangian. I guess that's a good place to stop. I'll come back and talk about weak scale supersymmetry, construction of the supersymmetric standard model, issues associated with that. Okay, anybody questions before we head out? Nope, let's stop there.